Okay, first I want to tie up a few loose ends from section 4.3, mostly having to do with interpretations of these definite integrals. Okay, so far I've kind of been glossing over the fact we've said things when we first set up the definite integral. We said that f of x was a positive function. So then the definite integral of f of x was the area, I don't know where to draw it, area underneath the curve. So if f of x is positive, our curve's up here, and so it makes sense to say, like, between a and b, what's the total area that's trapped under the curve and between the curve and the x-axis. And that's true. When we have a positive function, this definite integral represents this. However, it can also be made sense of if f of x is not necessarily positive. So let me talk about that first. So if we've got a curve that's sometimes positive and sometimes negative, or allowed to be negative, then what does it mean if we take the integral from a to b? So if this is our f of x function, the integral from a to b of f of x it has to do with area, but we have to allow for the possibility of negative area. So what that means is area, we look at the curve and the x-axis. So between a and b, we look between a and b, between the curve and the x-axis. When the curve is above the x-axis, like it is here and here, that area is treated as being positive area. So whatever this region is, it has a positive area. And whatever this region is here, it has a positive area. So those are positive. Any place where the graph is below the x-axis, so has negative values, that region is we interpret as having negative area. So it's not a geometric area. It's given an artificial sign, so it's negative. So this integral is the net area overall. So if we could do it geometrically, we'd figure out this area and add those, and we'd figure out this area and then subtract it from the other two. So in general, the definite integral is the net area, where regions above the x-axis have positive area and regions below the x-axis have negative area, and then we just add those things up to get the net area. Okay, so let's look at a specific example just to illustrate with something concrete. So, for example, suppose we had, let me be more careful with my size here. The integral of, let's say, 2 minus x dx from 0 to 3. Okay, so let's compute this with our fundamental theorem of calculus from the previous video first, and then we'll think about what the graph looks like. Okay, so we would integrate this 2x minus 1/2 x squared. That's our antiderivative, and now we plug in our 3 and our 0 and subtract. So let's work this out. If you plug in 3, that's 2 times 3 minus 1/2 3 squared, minus, now if we plug in 0, we get 2 times 0 minus 1/2 0 squared, which just comes out to be 0. So that's 6 minus 9 over 2 6 is 12 over 2. So we get a total of 3 over 2. So our answer to this integral is 3 over 2. Let me record that and then erase the work. Now let's think about the same problem, but let's look at it from a geometric standpoint. So we did one or two like this a few weeks ago. Let's compute what this should be from our definitions and understanding of definite integrals. So 2 minus x. That's a line with y-intercept 2 and slope 1. So in x equals 2, we're on the x-axis. But we're going from 0 to 3, so we need to go out to 3 here. So in x equals 3, 2 minus 3 is negative 1. So our final point is down here. So our graph looks like this. Okay, so let's compute the integral geometrically now. There's two parts to it. There's the triangle up here. That's a triangle with height 2 and base 2. So this area here is going to be 1/2 base times height. It's 1/2 base times height. So base times height's 4, so 1/2 is 2. This area here is 2. And it's a positive 2 because it's above the x-axis. Our second part of our region, or second part of our integral, is this triangle down here. I guess I should shade it. That's a triangle. Its height is 1, its base is 1. So 1/2 base times height. Base times height is 1 times 1. 1/2 will make this a 1/2 area. But it's a negative area because it's below the x-axis. So my net area would be a positive 2 and a negative 1/2. So 2 minus 1/2, that's 4 over 2 minus 1 over 2, that's 3 over 2. That's exactly what we got here with our computation. Okay, so in general, when your definite integral is a positive number, that means your graph has more area above the x-axis than below. If your integral comes out to be negative, that would mean there's more below the x-axis than there is above the x-axis. If it came out to be exactly 0, that would mean there's exactly the same amount of area above as there is below. So the two are equal. They cancel with each other. All right, so moving on to a little bit more application focus. What do these things represent in real world or application problems? Okay, so let's do a word problem. A car travels with velocity. I'm going to have to erase this before I do the work anyway, but a car travels with velocity v of t equals 20 square root t plus t miles per hour. Where t is the number of hours that have passed. So at t hours. So it's not meant to be realistic. It's just to give a concrete example of with units mostly. Okay, so the question is, how many miles does the car travel between t equals 1 hour and t equals 4 hours. Okay, so I'll erase this so I can work it out. But think about what we're after. We're after how many miles does the car travel. The function we have is miles per hour. So the function is velocity, and velocity in this example is measured in miles per hour. We want to know how many miles. And so the way we think of that, these two units, this is our main hint, these two units, they differ by a per hour. And so we know when we're taking derivatives, when you take the derivative of a function, you introduce a per whatever the input unit is. But that's what we start with here. We want to get rid of the per. So the opposite of taking a derivative is taking an integral. So if I want to answer a question about miles, and I'm given miles per hour in my function, that suggests I want to integrate. Because when you integrate, when you take an antiderivative, you lose per. You're multiplying by your input units. Sorry. I wasn't having this much trouble with keeping it standing straight the other day. So what was it? When you integrate, you are basically multiplying by your input units. So if you have miles per hour and you multiply by hours, you lose the per hour and get miles. All right, so all that being said, another way of thinking of this is if I'm dealing with velocity or speed, speed is the rate of change of distance. Distance is what we're trying to find. We're trying to answer a question about distance. So velocity is the derivative of distance. So if I want to figure out distance from velocity, that means I'm taking an antiderivative or an integral. Okay, and once we recognize all that, then what this tells us to do, I'll write this before I erase. We want to integrate our velocity function, v of t. I'll rewrite it when I work it out. We want to integrate our velocity function, v of t, from our starting time of 1 to our ending time of 4. So we're integrating v of t from 1 to 4. Okay, so let me erase the words here so I can get the function. Well, you have it written, I have it written, so let me erase this. So we're integrating from 1 to 4, our velocity function. Okay, so our velocity function was 20 square root t plus t. This would be dt since the variable's t. All right, so now to integrate this, again, like we talked about last time, anytime there's a square root or any root and we're integrating or taking derivatives, we want to first rewrite it as a power function. So that's 20 t to the 1/2 plus t dt. And now we take the antiderivative. So t will become, or the power will become, we add 1 to our exponent, so it becomes 3 over 2. And then since it's a fraction, we multiply by its reciprocal. So I'm going to multiply 20 by 2 over 3. That'll be 40 over 3. And then t, when we integrate that, that becomes 1/2 t squared, as usual. Okay, so we took the antiderivative. Then we have our t values, 4 and 1. 4 goes at the top, 1 is at the bottom. And so we plug in 4 first. So now we really have to be careful because there's multiple terms and we have non-zero numbers. So we really have to be careful about signs and subtraction. So we have 40 over 3 4 to the 3 over 2 power plus 1/2 4 squared. That's what I get when I plug in the top number to this function. Then I subtract what I get when I plug in the bottom number. So I need to be careful with parentheses here. Minus parentheses, this whole function with 1 plugged in. So 40 over 3, 1 to the 3 over 2, plus 1/2, 1 squared. Let's go through the simplification. Okay, so again, when we deal with a fractional exponent, first apply the denominator as a root. So I'm going to take the square root of 4. So that gives me 2. Then I have to raise that 2 to the 3rd power because I still have that numerator to deal with. So 2 cubed. So I'll have 40 over 3 times 8 plus 1/2 times 4 squared. 4 squared is 16. This one's easier. 1 to any power is 1, so this will be 40 over 3 times 1. 1 squared is 1, so we have plus 1/2. So let me erase these steps at least. Okay, so that's going to be 40 times 8 is 320 over 3. 1/2 times 16 is 8. How do we want to do this? Let's distribute, rather than simplify this, because we'll have to do fractions at some point, but let's distribute the minus sign. So minus 40 over 3 and minus 1/2. All right. Where does that leave us? Let's combine like fractions here. 320 minus 40 is 280. Let's do the 8 and the minus 1/2. 8 is 16 over 2, so that'll be 15 over 2. And now we can get the common denominator here. So multiply the first one by 2 over 2. That'll be 560 over 6. Plus 3 times 15 is 45 over 6. So 605 over 6. Which is going to be, just make it easy, that's 100. That's as a mixed number, 105/6. And again, this is miles. Because our velocity was miles per hour. When we integrate it, we get something in miles. We lose the per hour because hour was the unit on our t. Okay, so these definite integrals, in application problems, these definite integrals, the thing you're integrating, the function you're generally integrating in an application problem is a rate of change. It's got a per something, a per dollar, per unit, per hour, whatever. So when you integrate it, you lose that per. So you're figuring out a net a total change, a net change in your underlying function. Okay, so we're dealing with velocity here. That's the derivative of distance. So when you integrate, you get a net change in distance. How far your distance changed between these two times. All right. So let's erase that. And let's start talking about some other applications of integrals, or I guess not. The section 4.4 is called Properties of Definite Integrals, but it'll include some applications. So properties of definite integrals. So we've already talked about properties of indefinite integrals, like they preserve addition or subtraction and things like that. I don't want to repeat those. I want to talk about some things that are specific to definite integrals. So the first is the additive property, which doesn't mean the same thing as it might have for indefinite. And so what it says is, let's draw the picture first. If I've got a function y equals f of x, and I start at a and I end at b, the area from a to b, that's the integral from a to b. So this red, I hope it shows up as red, I don't know. This red region, the shaded region, that is the integral from a to b of f of x dx. Now suppose I picked another x value, and just to make the picture easy, let's suppose we have a third x value that's somewhere in between, and call that c. Then what I could do is I could split my region at c. So I'd go from a to c, there's one region, one area, and I go from c to b, there's another area. Together, those two areas give me the total area. So what I can do is I can split my integral into two separate integrals, one from a to c and one from c to b. So integral from a to b, sorry, a to c, f of x plus the integral from c to b. I hope that's legible. I'll rewrite that, sorry. I'll write in the next line. So this is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Okay, so the obvious question is, why would we want to use, in what circumstance would we need to use this? I mean, it's clearly true from the picture. It's also, I mean, it's even true if c was out, well, let's not get into it, but if c was any number, even if it was outside the region, this would still work. But the real reason you want this is for situations where you don't really have an antiderivative that works for the entire interval. So, for example, piecewise functions are the big situation where this is relevant. So suppose f of x is the function. It's the piecewise function. It equals 3x if x is less than 2, and it equals 10 minus x squared if x is greater than or equal to 2. Alright, so if I were to graph this, I don't want to spend too much time on it, but if I were to graph this is a piecewise function. So from 0 to 2, for example, it's a straight line with slope 3. So it's like that. From 2 onward, it's now a parabola. 10 minus x squared is a parabola that opens downward. It's going to be like this. So it's now a curve. So there's a corner, there's a sharp corner right there at x equals 2. And so if I want to integrate from something before 2 to something after 2, it's really two different functions I'm dealing with. And it's possible that I could figure out a single antiderivative that works for the whole thing. It's tricky because it's going to be a piecewise function, and you have to worry about making it continuous and so on. So we don't want to do that. We don't want to do it as just one step. Instead, let me actually write the problem. I haven't written the problem yet. Let's integrate this function f of x from 0 to, let's say, 5. Okay, so the issue is this function changes once you hit 2. Before you're at 2, before x is at 2, it's 3x. After 2, it's 10 minus x squared. So what I want to do is split up my integral at 2. I go all the way from 0 to 5, but I want to go from 0 to 2. And then I want to go from 2 to 5. And by my additive property, it splits up as a sum of these integrals where it breaks up at 2. But now the point is, this first integral, it's applicable for every x value between 0 and 2. So between 0 and 2, we're using the formula 3x, because that's applicable whenever x is less than 2. Now, it doesn't matter that at 2 you actually switch. Integrals don't care what happens at a single point. Just like with limits, if you change the value at one point, it doesn't affect the area. It's not affecting anything significant. So all that matters is what is the formula between 0 and 2? It's this. So this first integral would be the integral of 3x dx from 0 to 2. The second integral from 2 to 5, on that interval, x is bigger than 2, so we'd use 10 minus x squared as our function. Okay, now we essentially have two integral problems. We do them separately and then just add them together and we get our final answer. So let's go ahead and do it since we haven't done that many examples yet. But I'll have to erase somewhere along the way. Okay, so this one first. 3x squared, that would become 3x would become 3x squared divided by 2. And we evaluate that between 0 and 2, or from 2 to 0. This one, 10 would become 10x minus x squared would become negative x cubed times 1/3. And for that one, we plug in 5 and 2. Okay, so now we plug in our values. So 2 and 0, we're just plugging into this function here. So we get 3 over 2 times 2 squared minus 3 over 2 times 0 squared. That was this function. Now this one we have to be more careful because it's got multiple terms. First I plug in 5 to both of these. So we have 10 times 5 minus 1/3 5 cubed. And now I subtract, let me do it on the next line, minus, I'm going to plug 2 into this function. 10 times 2 minus 1/3 2 cubed. All right, so now simplifying. 0 squared is 0, so that disappears. But we'll have 4 times 3 over 2. 4 divided by 2 is 2, so this will give me 6. Minus 0 plus, let's simplify these. 10 times 5 is 50. 5 cubed is 125. So 125 over 3. Minus, this will be 20 minus 8 over 3. Okay, so now let's carefully deal with the minus signs. Let's do the whole numbers first. That's the easy part. You have 6 plus 50 minus 20. So that's 50 minus 20 is 30. 30 plus 6 is 36. Now I've got minus 125 over 3. And minus makes plus 8 over 3. So that's 36. Negative 125 plus 8 will be negative 117 over 3. Let's see. 36 times 3 minus 117 is negative 9. So this turns out to be negative 9 over 3, which is negative 3. Yeah, so that's our answer. That tells us that the graph of this piecewise function between, what was it, 0 and 5, yeah, we've integrated from 0 to 5. The graph of this piecewise function has more area underneath the x-axis. So my drawing before was incomplete. The scale is off, but if I drew this, you've got a line at first, and then once you hit 2, you've got a downward opening parabola. It goes down like this, and by the time we get out to 5, I don't know what my scale is, there's more area down here than there was up here. So the stuff down here overpowers the stuff up here and gives you a negative answer for your integral. All right. So there's our piecewise trick. When you're integrating a piecewise function, you split it at the, if necessary, you split it at the x value where it changes. Okay. We got 33 minutes. I'm trying to decide what to do with our remaining time. Let's do another a related example. Suppose you're integrating a function from 1 to 6. The function is absolute value of x minus 3 dx. Okay, so the easy mistake to make with these is basically trying to like ignore the absolute value. Okay, so it would be a mistake to write absolute value of 1/2 x squared minus 3x. Integrals do not respect absolute values. Okay, so instead, let's think about so this is a side comment here. Absolute value of x minus 3. Let's think of what this function really is. So what the absolute value always does is it forces your output to be positive no matter what's going on the inside. So if the inside is already positive, the absolute value doesn't do anything. So this would equal x minus 3 if x minus 3 is positive. X minus 3 is positive when x is greater than or equal to 3. Or it's non-negative when x is greater than or equal to 3. On the other hand, if x is less than 3, the absolute value, if x is less than 3, then x minus 3 will be negative. And the absolute value will make it positive by basically flipping the order of subtraction or multiplying it by -1. So you get 3 minus x in that situation. So 3 minus x would be positive when x is smaller than 3. Okay, so absolute value functions are really a kind of hidden piecewise function. You rewrite the absolute value as two cases, opposites of each other. The function itself, and then it's negative. And it splits at the x value that makes this inside function 0. As long as it's a simple linear function like this one is. All right. So what that tells us is our integral, we want to rewrite it just like we did the last one. Rewrite it as two separate integrals added together. But this time, it changes when x is 3. So we're going to go from 1 to 3, and between 1 and 3, this function is determined by 3 minus x. If we're between 1 and 3, x is less than 3, so we'd use this formula, 3 minus x. And then we plus the integral the rest of the way, 3 to 6. And between 3 and 6, x is bigger than 3, so we'd use x minus 3 as our formula. Right? So again, we've got two integrals to evaluate. I'm going to do my next step above this. Integrate 3 minus x will be 3x minus 1/2 x squared. That'll be 1 to 3 plus the integral of this will be 1/2 x squared minus 3x. And that's from 3 to 6. Now another common mistake that could be made is it looks like these are opposite functions. So it's tempting to say, well, you have negative x and plus x, and those cancel. We have 3 and minus 3, those cancel. But I can't combine them because I have different bounds on their integrals. And so you see here, it's not that I have 3x and minus 3x. They're not, and they're like terms, and they can cancel each other. Because I still have to plug in these specific values. This x is taking these two values. This x is taking these two values. So I have to treat these as separate problems before I think about combining them at all. I have to simplify the separate problems before I can combine them. Okay, so plug 3 into this. We got 3 times 3 minus 1/2 3 squared minus, now plug in 1, 3 times 1 minus 1/2 1 squared. So that's this part. And I'm going to add 1/2 6 squared minus 3 times 6 and minus 1/2 3 squared minus 3 times 3. Okay, so now carefully work this out. And you see there's not that much simplification. So for example, I've got this 3 times 3, and I have a minus 3 times 3. So those don't cancel because they'll both be positive. So let's be careful and just simplify each of the parentheses. This first parenthesis will be 9 minus 9 over 2. This will be 3 minus 1/2. This will be 6 squared is 36, divided by 2 is 18. Is that right? 30, yeah. 3 times 6 is 18. So this one at least is 0. And then minus 9 over 2 minus 9. All right. So 9 over 2, 9 minus 9 over 2, that's 9 over 2. This will be oh, I'm looking at the wrong answer. All right. 3 minus a half is 6 over 2 minus 1 over 2 is 5 over 2. Plus 0 minus 9 over 2 minus 9, that's negative 9 over 2. So putting this all together, that's 9 plus 9 is 18, minus 5 is 13 over 2. That's right, yeah. Right, so our final answer to this integral is 13 over 2. Okay, so past 40 minutes now, so rather than start another topic, let me just pause and say where we're at. So the way the homeworks are set up on my math lab, our homework 11 covers sections 4.3 and 4.4. We've finished 4.3 completely. We've done part of 4.4. There's still a couple things to talk about with 4.4. I should record more videos soon. I don't know exactly what day. I don't know exactly have a schedule worked out for when I'm recording. I'm still working out the bugs in my system here. In any case, I recommend after you watch these first two videos, you start looking at homework 11 if you haven't already. I've changed the due dates on the My Math Lab homeworks. I don't remember I set them far off in the future because I don't really want to worry about due dates because of how these videos are working. I don't know how it's going to work out. So you can pretty much work at your own pace, according to what videos I put out. They'll be due at the end of the semester before the final exam, essentially. If I have to change them again, I will. But start looking at homework 11. You won't be able to do everything until I have the next video out, which will be hopefully by the end of this week. But we'll see. So for now, look at homework 11 and await the next video.